Beneath the glittering skin of the ocean lies a realm few have ever seen. A silent expanse that stretches endlessly, where sunlight dies and pressure rises high enough to crush metal. In this kingdom of cold darkness, life doesn't merely persist, it transforms. Tiny creatures that should fit in the palm of your hand grow into monsters of myth. Shrimp as long as your forearm, jellyfish with bells wider than a doorway, and squids that stretch the length of a city bus, gliding through the blackness like ghosts. This remarkable phenomenon has a name: deep-sea gigantism. Scientists have documented it for decades, yet the full mystery remains unsolved. Why does the deep favor giants? Is it the freezing temperatures that slow life's rhythm, the crushing weight of the abyss, or perhaps something hidden in evolution's deeper code, the instinct to grow when the world above would rather see you vanish? Today, we descend into one of the ocean's greatest enigmas. We'll meet the giants of the deep and uncover the strange forces that shape them into the titans that roam beneath our world. Deep-sea gigantism isn't imagination, it's measurable fact. Across species living below 1,000 meters, scientists have found consistent evidence of enormous body size. Take the giant isopod, for example. Picture the little pill bug that rolls into a ball when you touch it. Now enlarge it to the size of a small puppy. That's Bathynomus giganteus, an armored scavenger crawling through the abyss. It can reach half a meter long and weigh over a kilogram, feeding on decaying remains that drift down from above. Then there's the Japanese spider crab, a slow-moving relic that prowls the seafloor with legs spanning nearly 4 meters. Its body is small compared to its reach, yet its long limbs make it the largest arthropod on Earth, a creature that seems engineered for a slower, stranger age. And, of course, the colossal squid, the most elusive of them all. Seen only in fragments or fleeting glimpses, it's believed to be the largest invertebrate alive. Its eyes, each the size of a basketball, are the biggest in the animal kingdom. In the pitch-black waters of the Midnight Zone, those enormous eyes are the difference between life and starvation. Even the smallest creatures undergo transformations here. Tiny amphipods that barely measure a centimeter in shallow waters grow to the length of a ruler in the Mariana Trench. Giant jellyfish drift with bells as wide as a person is tall. Tube worms at volcanic vents grow 2 meters long without mouths or stomachs, living off the bacteria that thrive inside their bodies. The deeper we go, the bigger life becomes a reversal of nature's ordinary logic. Why does size seem to bloom where light cannot reach? The answer begins with temperature. Down here, the ocean rarely rises above 4 degrees Celsius. Cold slows everything: metabolism, movement, even aging. In a world where food is scarce, a slow metabolism becomes a superpower. When you burn energy slowly, you can endure hunger longer, hunt less, and simply wait. Waiting is survival in the deep. Another crucial factor is oxygen. Cold water traps more dissolved oxygen than warm water. For massive bodies, oxygen is life's currency. In tropical waters, growing too large becomes a liability. Your tissues can't get enough oxygen to function. But in the icy depths, oxygen flows freely, supporting larger bodies that would suffocate closer to the surface. Then there's pressure, a constant, unimaginable force. At 4,000 meters below, the ocean pushes with 400 times the pressure of the atmosphere. For most creatures, it would mean instant collapse. Yet for the deep dwellers, it's normal, and perhaps beneficial. Larger animals handle pressure differently. Smaller creatures, with more surface area relative to their volume, suffer greater cellular stress. Bigger bodies distribute that pressure more efficiently, keeping their internal structures stable. Add to that a principle called Bergmann's rule, the tendency for larger bodies to conserve heat better in cold environments, and you begin to see why the deep rewards the slow, the dense, and the giant. But there's another truth hiding in the darkness. Food is rare. Sunlight fuels life near the surface, feeding plankton and fish in an endless cycle of energy. But beyond 1,000 meters, photosynthesis ends. Down here, life survives on marine snow, a slow blizzard of organic dust drifting from above. Dead plankton, fish scales, and waste particles rain down continuously, though most are devoured long before they reach the abyss. What arrives is barely enough to survive on. Sometimes, however, a feast arrives, a fallen whale, or a giant fish carcass, and entire ecosystems bloom around it. These rare windfalls can feed hundreds of organisms for years. In such a desert, survival means mastering patience. Large animals, with slower metabolisms, need fewer meals to sustain them. The giant isopod can go a year without food. The Greenland shark, a deep-water species, grows at a glacial pace and may live more than 400 years, the longest lifespan of any vertebrate known. In the deep, time itself slows. Growth is measured not in seasons, but in centuries. Being big down here isn't about dominance, it's about endurance. To grow large is to endure long stretches of famine, to outlast the hunger of the abyss. Size also offers protection. The deep sea may be vast, but its predators are few. There are no sharks or dolphins hunting in these depths. The hunters here are ambush specialists, anglerfish with glowing lures, dragonfish with invisible red beams, gulper eels with expandable jaws, but even these fearsome predators have limits. A giant isopod, encased in armor, presents too much trouble for the reward. The Japanese spider crab, despite its delicate appearance, can fend off smaller attackers with its reach. Even jellyfish benefit. The big red jelly floats unbothered through the abyss, its thick arms loaded with toxins, too large for most fish to consume. There's even a theory called the predation release hypothesis, which suggests that in low predator environments, prey species evolve to be larger. In shallower waters, small size means safety, you can hide or flee. But in the deep, where hiding is impossible and energy precious, growing large becomes the better defense. The deep sea is the oldest, most stable environment on Earth. It doesn't change with seasons or storms. Temperature, pressure, and darkness remain constant for millions of years. In such stability, evolution slows, refining creatures rather than reinventing them. Many species here are living fossils, nearly identical to their ancestors from the age of dinosaurs. The giant isopod's lineage, for example, stretches back over 160 million years. In these quiet depths, with little competition and vast open space, there's room both physically and genetically to grow. Evolution favors patience. Growth happens slowly. Reproduction happens rarely. Many deep-sea species follow K-selection, producing few but well-developed offspring. They invest energy into survival rather than numbers. In a world where stability reigns, this strategy works perfectly. Now we know these monsters are not beasts of legend, but survivors of an ancient world. They aren't terrifying because they are evil, they're awe-inspiring because they exist at all. What's truly monstrous is not the creatures, it's the scale of the ocean itself. Humanity has explored less than 5% of it. Every new expedition, every submersible dive reveals something no one has ever seen before. The myths were wrong in detail, but right in spirit, the deep really does hold giants. So why do deep-sea creatures grow so huge? The reasons intertwine: cold, pressure, oxygen, scarcity, stability, each shaping life in ways we barely grasp. But beyond the science lies a deeper truth: life always adapts. What thrives in coral reefs would perish in the abyss. Yet in that silent, crushing dark, life finds another path, slower, larger, stranger. The giants of the deep are proof that there is no single way to survive. Every descent into the abyss gives us new questions. We discover creatures larger than we predicted, living in places we thought were impossible for life. The deep remains the planet's final frontier, vast, mysterious, and full of stories still untold. And every time we uncover another giant, it reminds us of something simple yet profound: that life, no matter where it's found, will always find a way to grow, endure, and astonish.